Hello everybody, and welcome to the third video of the TypeScript Engine tutorial series. So if you recall, last time we actually initialized OpenGL, got ourselves clearing to a black screen, and did a little bit of house cleaning and code cleanup along the way. And what we wound up with was something that looks like this. Well, let me just reload that. So what we wound up with was a really small canvas that is just sort of up in the corner of the screen. It doesn't resize with the browser. It doesn't really do much of anything. So what we want to do is we actually want to make this a little bit more dynamic so it uses the entire screen so we can kind of see what we're doing a little bit better. So we're actually going to go ahead and fix that right now. So what we're going to do is we're going to actually start off with some CSS. And CSS is just used to style the elements of a page in such a way that we don't actually have to do these things in code. And so what I'm actually going to do is add a style tag, and we're going to say the type is text CSS. And within this tag, we can actually declare some CSS code. So I'm not going to do a whole lot of fanciness here. I just want to put some basic things in just to make our page act the way that we want it. So the first couple things I'm going to do is I'm going to remove some defaults that are put in there by every browser that we actually don't want. And that is on the HTML element and the body element. So the syntax of CSS is a little bit strange. If you want to, go ahead and read up on it. I'm not really going to go into it here because it's not a focus of this tutorial series, so just kind of take this at face value and we'll go from there. So what this is basically saying is we want to apply this style to both the HTML and the body element. And we want to take padding and set that to 0, because padding is actually what is causing that border sort of around the page that shifts it over by about 10 pixels. So if we run this and refresh, oh dear. I think it's margin, actually, is what I want. Yes, margin. Okay. So it's always a good idea to reset both. But you can see what this has done is this has actually shoved that element right up into the corner of the screen, which is what we want. So you always want to reset your margin and padding to 0 because we just don't want that border around here. It gives us a nice way to sort of expand the element to the whole screen. And the next thing we want to do is we want to actually apply some styling to the canvas element itself. So we say canvas, and in that we say the width is 100%, and the height is also 100%. And we run that, and you'll note that we now have a full screen canvas. So the interesting bit here is we have some weirdness when it comes to the way that this canvas is actually resizing on the screen. So unfortunately, CSS doesn't quite give us what we want. What this is actually doing is this is actually maintaining a specific aspect ratio, which is a height to width ratio. And for some applications that may be okay, but in our case it's not really what we want. We want it to actually stick with a full screen. And so what we're actually going to do is we're going to use a little bit of JavaScript to sort of override that. And we're going to do that by capturing the Windows resize event. So for now, I'm just going to put this in app.ts. I may wind up moving this later to a different class that's a little bit more appropriate for it. But for now, I'm just going to actually just do this in straight JavaScript. So I'm going to say window.on resize. And we're going to take a function, set that to a function rather. Okay. And in our engine, we're actually going to have a public method and we're going to call that Resize. And we're not going to worry about taking in any properties. We're not going to return anything. We just want to call it. And we're going to say here, resizes the canvas to fit the window. Okay? And let me close this. So back here in app.ts, we are actually going to modify a couple of things here so that we can actually handle this event properly. So right now we have just a local variable called engine. For the purposes of this, for now, we actually need to make a global. So I'm just going to call this engine, but I'm going to have it stored as a var, global var rather, and it's going to be of type tse.engine. And I'm going to remove the let here. So now what this is actually going to do is it's going to be referencing this, and you can tell by the highlighting which variable it's actually using. And what that will allow me to do is say engine, if I could spell, .resize. And that's all we want to do. We just want to take this event that's passed from the window, from us resizing it around on the screen, and we want to tell the engine, hey, resize yourself, every single time this is called. So back in the engine, what we actually want to do is we want to first check to see if the canvas is not equal to undefined. And that might be because the browser could kick off potentially a resize event before we've initialized this code here. In fact, it's extremely likely that will happen. So we want to just guard against this not yet being defined by the time this code actually runs. So what we want to do here is we want to say this.canvas.width equals window.inner width. And what inner width is the actual size of the client space in the browser. So if I open a browser here, so the window.inner width is actually this whole space here, all these corners here. And so it doesn't actually include the size of this title bar or any of the tool panes up here. It's just this section here. So that's what we want. So we also want to set this.canvas.height equals window.inner height. And that will sync up the size of the canvas to the size of the window. So when we resize, now it sort of resizes like we expect. However, you'll notice that there's some issues here with the scroll bar. And the reason for this is the code that actually is calling our resize isn't always 100% accurate in terms of what it passes through, because this resize event gets called many times per time you move it or resize the window. And so many times it'll actually get it right, but sometimes it'll actually get it wrong, and it'll actually put this scroll bar here, which kind of screws things up. So to fix that, we need to actually go back to our HTML page, and here we just want to say in the HTML and body, we just want to say overflow hidden. And this will make sure that those scroll bars don't appear. And so now, if we resize this, we don't get the scroll bars, we don't get the weirdness on the page, it resizes correctly every single time. So it's a quick, nice, and easy way to get that resizing to happen. Now, there's a couple things that we could change here. If we wanted to have the, maybe these white flashes not show up, we could set the page's background to black, but I'm not going to bother with any of that for this. If you want to do that on your own, go ahead. But for now, I think this is actually okay. So now that we've got our window straightened out, I'm going to go ahead and close this page here. And the next thing that we want to do is we actually want to start rendering something to the screen. But before we can actually render anything to the screen, there's a couple of steps that we have to take first. So the way that WebGL works is it draws things to the screen using something called shaders. And shaders are small programs that are written that are sent directly to your graphics card, that the graphics card is then able to optimize and run very, very quickly to draw things to the screen. So it's a way that gives us complete control over what is drawn to the screen. And it's a super powerful thing. It's a little complicated to set up at first, but once you've got it set up, it's really straightforward to use. And so we actually have to create these shader programs and tell WebGL that we want to use them before we can actually draw anything to the screen, because otherwise WebGL has no way of knowing what we want to draw to the screen or how it wants to be drawn. So we actually need to set some of those things up. So in order to do this, I like to wrap the shader logic in a class. So all of that stuff is abstracted away. You don't have to worry about the inner details of that shader. All you have to do is call a couple methods on it, and it just figures out what it needs to do internally and handles itself. So what I want to do here is actually, I want to organize things a bit. So I actually want to create a folder here called core. And this is going to contain things that are core to our engine, that our engine is going to make use of. And what I'm actually going to do is I'm going to put engine in the core because it's part of the core itself. And inside core, I want to create another folder, and I want to call that graphics. And I'm not going to put anything in there just yet, but we are going to be putting things in there. And the next thing I want to do is I want to create another one called GL. And so all the WebGL specific stuff we want to actually put in this GL folder, because we want to actually abstract the GL API away as soon as we possibly can. And what I mean by that is we want to create our classes in such a way where they wrap around all that stuff that happens in WebGL, all that low-level code, so that we don't have to worry about it anymore. We can just call a couple of simple methods on the surface and be done with it. And so the sooner you get that stuff abstracted away, the better. And so that's what we're going to do here. So I'm also going to move this GL into the GL folder. And let me just save everything real quick to make sure that doesn't get lost. And in the GL folder, I actually want to create a new TypeScript file, and we're going to call that shader. And so we're going to use namespace TSE. And we want to export a new class called shader. Okay, so as I was talking about shaders before, I mentioned that shaders are tiny programs that get uploaded to the graphics card. So obviously every program that runs at any level has source, right? This application that we're writing here has source. Shader programs have source too. And for most shaders in WebGL, there are two types of source that you're going to need. There is vertex source for a vertex shader and fragment source for a fragment shader. And a vertex shader basically takes in information and works out things positionally in 3D space. And that is where the translation from 3D space to 2D space, which is what your screen is, happens. All that stuff happens in the vertex shader. And then that positional information is then passed on to the fragment shader, and the fragment shader actually determines what colors are written to the screen. And so what you're actually representing may involve 1 pixel, it may involve 10 pixels, it may involve the entire screen, but it's what actually outputs the color. So the vertex shader deals with positional information, and then the fragment shader takes that positional information and outputs it to something that the screen can actually use. It outputs color. And so it's important to distinguish those two things. And so in our constructor, we want a public constructor here. We want to take in the source for those two shaders. And of course the source is going to be represented by a string. So we're going to say vertex source, and it's of type string. And then we're going to say fragment source, which is also of type string. Okay, and before we can do anything with that, what we want to do is we actually want to create a couple of private methods. So we want to first create a private method called load shader, and that is going to take in source, which is a type string, and it's also going to take in a shader type, which is of type number. And we're actually going to return a WebGL shader. And so what this is going to do is this is going to take one of these sources, load it up, compile the shader, and return a WebGL shader object. And it's going to be of type shader type, whichever type we pass here. You'll sort of see what I'm going to do with this in a minute. So here we're going to say let vertex shader equal this.load shader, and we're going to say vertex source, and we're going to say GL dot, why isn't GL coming up? Oh, I had a period there. GL dot vertex shader. Right? So GL dot vertex shader is a number internally, but it's basically telling this what type of shader we want to load. Right? So next we're going to say let fragment shader equal this dot load shader, fragment shader, and fragment source, and it's going to be of type GL fragment shader. Okay, so this is going to be very reusable code. We're actually going to use the same code twice here. And so in this method, what we want to do is first set up a shader of type WebGL shader. And we're not going to assign anything to it yet, but just to get rid of this error that's coming up here, we're going to return shader. Now right now, obviously, if you run that, that's gonna throw some errors. It's not really going to do anything. It's going to return undefined right now, actually. And so we actually need to fill this out. So we need to call a couple of WebGL methods to actually make this happen. Okay, so the first thing that we actually need to do is actually, instead of leaving this undefined, we can actually say gl.create shader, and we just pass it the shader type. There we go. So now GL knows that we're going to create a shader. And so the next thing that we do is we say gl.shaderSource. So we're actually going to be passing the shader source to WebGL to actually do something with. So we're saying this is the source of this shader. And so we pass the shader as the first parameter, and then we pass the source as the second parameter. And the next thing that we're going to do is say gl.compile shader, and we're going to pass a shader again. And so basically it's going to say take the source that you have been given and compile it. And the next thing that we're going to say is gl.get what was it called? Shader info log. And we're going to pass it shader. And that returns a string, so we want to hold on to that. So basically the way that this works is the shader info log, if there's an error, this is going to capture it. And it's going to set it to set error to that string that gets returned. So what we want to do is we want to say if error whether is not equal undefined, we want to throw a new error, error, and we want to say error compiling shader, and then we actually want to output the message. So we'll say error. Okay. And if that's the case, it's going to stop the application because we're not going to be able to run without our shader. So we definitely want to use a throw here. Okay. And if that all goes correctly, it's just going to return that shader, and that's going to be it for that step. So we load our vertex shader and our fragment shader. So at this stage, there's actually a couple more things that we need to do before we can move on. The first of those things is we actually should take in a name of the shader, which is just of type string. And this will be a way for us to identify shaders when we have more than one of them, because we can have more than one shader. We can have a bunch of shaders. Another engine that I've written in the past, I think, is up to 8. So it's a good idea to be able to identify the shader somehow, and name is one of the clearest ways to do that. So I'm just going to create a private name of type string. And I'm going to say this dot name equals name. And let's go ahead and add a public accessor. So we'll say public get name turn type string turn this dot name. Now, for those of you who are wondering why I didn't just create a public name and just have it just be public instead of using a getter like this, I want it to be read-only. I don't want the name to be modified outside of the shader after it's created. So let me just put some comments in here. The name of this shader, and on the constructor creates a new shader. The name of this shader, the source of the vertex shader. And I'm just going to copy that. And we'll say the source of the fragment shader. And that's a WebGL shader. Okay, so that's all nice and created. So one thing that this also allows us to do is output the shader name in the string here. So we can actually say, we can put some single quotes and double quotes, plus plus, this dot name. So now we can say error compiling shader, whatever name we pass in, and then spit out the error. So it's just a little bit better error reporting. So the next thing we're going to need is another private method, and we're going to call that method private create program. And we're going to return type WebGL program. And so a WebGL program is, WebGL, I thought it was it's WebGL program, okay. A WebGL program is the result of taking these different shaders that have been compiled and linking them together, and that's ultimately what the graphics card winds up using. So we need to save a private program of type WebGL program, and I think you can kind of see where I'm going with this. Now we can say this dot program equals this dot create program. And we actually need to pass 2 WebGL shaders. So we'll say vertex shader, WebGL shader. Misspelled that there. Fragment shader, WebGL shader. And so we can just pass these things in here. Just copy and paste those. Oops. That should be a single equals, not a double. I apparently can't type today. Sorry about that. Okay. So what this needs to do is we need to say gl.create program. And we need to set this dot program to that. So we're saying, hey, WebGL, go ahead and create a program. Reserve a program for us. let's go ahead and just return. Actually, you know what? Since we're setting this .program, I don't need to actually do that. Let's make this return type void. We could just set the member from in here, and we don't have to do it up here. It's a lot more concise, I think. Okay, so what we want to do is we want to attach our shaders to the program, and then link the program. So to do that, it's just a simple gl.attach shader, and we pass it the program. So this .program, and we're gonna link attach rather the vertex shader first. I'm actually just going to copy this line of code and paste vertex shader in there. And now we're going to say gl.link program, and we're going to pass it the program. So this .program. So basically, we've attached these two shaders to it, and now we're linking the program. And this is what will actually allow it to be used. However, like we did up here, we should do some error checking just to make sure that everything went okay. So let's say the same thing. Let error equal gl.get program info log. This .program. And if error is not equal to undefined, we're actually going to do this same error, so I'm just going to copy it, except error linking shader. And so we'll say the shader name, spit out the error again. So this is everything that needs to be done to actually load up a shader. Now, you might be asking at this point, what the heck source are we going to use? And that's what we're going to do right now. So there's a couple of ways that you could do this. Some tutorials have you load it straight off the HTML page. I prefer to do it in code. You could reach out and grab a file that contains it. There's a bunch of ways that you can do it. I think the simplest way to do it, at least in the short term, is actually to just do it in code. So that's actually what I'm going to do. So in Engine, I'm going to temporarily create a shader variable, and I'm just going to call it shader. And the next thing we're going to do is we're actually going to create a private method called load shaders. It's going to be a return type void. And for now, this is only going to load one, but we might load others later on, so we're just going to call it load shaders. And we're going to say we're actually going to declare our shader programs. So the first one, we're going to say let vertex shader source equals. And then I'm actually going to use this grave character here to denote this string. And what this is it's an interpolated string. It accepts new lines. It accepts formatting, and it's a nice flexible format to hold source code for our shaders. So that's what I'm going to go ahead and use. And so the vertex shader source is very simple. It uses a language called GLSL, and you can read up on that, and we're going to go over some of the things that GLSL uses, but it's the language that WebGL understands to compile and eventually load in with shaders to the graphics card to be executed. So it runs just like most other programs. It starts with I think it's a VoidMain. I can't remember if it's an integer or void. One moment, let me look. It's void. Okay, it is void. Okay, so we don't take in any parameters, and we've got an open and a closed parenthesis. So here's where we're actually going to create our shader source that's going to be passed in. So we have this main entry point. This is where what the shader actually looks at to kick things off. And for the vertex shader, there's really only one thing that we're going to have to worry about, and that's called an attribute. So you have two things that shaders take as input. You have attributes, which is information about the vertex that you're passing in, And a vertex contains positional information. It includes maybe a color, or it includes some normal information, which is the direction it's facing. It includes a lot of different information that eventually we'll go over sort of one by one. So for right now, what I'm going to go ahead and do is just create one attribute, and we do that using the attribute keyword. And we need to give it a type. In this case, I'm going to give it a vector3. So this is a vector with 3 elements in it. In this case, it's going to be x, y, and z. And so what this will actually contain is positional information. So I'm going to call it a_position. And this is just to make it very clear that it's an attribute and its position. So this is the first attribute, and right now the only attribute that we're actually going to take in for this shader. And that's pretty much it. I did just realize, though, it doesn't belong in the main method. I apologize for that. It belongs above the main method, at the top of the source. So I don't know why I typed it down here. I normally don't do that, but whatever. So we have one attribute called position that we take in. It's a vector3. It gives us an x, y, z. So what the main shader does is its entire goal is to write out to a global variable that GL recognizes called GL_position. And case does matter here. So it's lowercase GL underscore capital position. And that is a vector 4. So it's a 4-element vector. So what we're taking in here is a vector 3. And so for this, we need to set it to a vector 4, which we can create by doing that. And then we can say a_position. And then 1.0 we can use as the 4th element in that vector. So we're setting GL position to a vector 4. We're using a position, which is the first 3 elements of that vector, and then a 1.0. So OpenGL actually allows you to shorthand it this way. The other thing that you technically could do is you could set it up like this. You could actually be explicit about it and say, well, I want to use aposition.x, and then for the second one, I want to use aposition.y, and then aposition.z. And this is totally valid as well. There's nothing wrong with doing it this way. However, it's a lot more concise to just do it this way. So that's what I'm going to roll with. This is all that's required for this shader for right now. We are eventually going to do other things with this, but for right now, this is all we need, is to just tell WebGL, this is the positional data for this particular vertex that we're trying to render. And I'll go into that a little bit more as we get a little bit deeper into this, but for now, just accept that sort of at face value. Next thing we want to do is we want to set up our fragment shader, shader source. And it's going to be the same process pretty much, except the formatting of this shader is going to be a little bit different. So it's going to have a lot of the same types of properties, but it's going to do something a little bit different. Remember, this is the one that's actually going to be writing out color. So we're actually going to take in the positional information that this is outputting, and we're going to deal with color in this scenario. So we don't take in any attributes, because attributes are actually used by the vertex shader. We can, however, take in uniforms, which I don't want to get into right now. We're actually going to come back to that in a bit. But what we need to do is we need to actually tell WebGL what our precision is. And we do that by using the precision keyword, medium precision. Oops. If I can spell. Medium precision. And we want to say that's the float type. So basically what we're telling WebGL is for the type of float, we want to set our precision to medium precision. High precision is used for on more high-end machines. You can use it on I think most machines will actually support it now, but WebGL doesn't actually have a default for this, so you actually have to set it for the float type. For some reason it doesn't have a default. I don't know why. It's just something you always have to do. So similar to our vertex shader, we have a VoidMain method, and it doesn't take any parameters or or have anything special about it. And its entire goal, similar to the vertex shader, is to write out to a GL underscore frag color variable. And again, this is a vector4, except it's a vector4 of color data, so RGBA like I talked about before. And so what we actually want to do here is, for now, we're actually going to set just a hard-coded color. We'll pass some color information here in a little bit, but for now, we just want to create a vector4, and we'll set everything to 1.0. And so, if you remember that scale of 0 to 1 for the RGBA that we used to clear the screen, this works exactly the same way. RGBA, they're all from 0 to 1. So by saying vector4 of all 1.0, which is this is the shorthand of it, again, you could say this, and it's the same thing. But what this is actually going to wind up to be, if you have ever dealt with this kind of stuff before, is white. So we're actually going to just output pure white for this, and that's it. Obviously, we're going to get a lot more advanced with this as time goes on, but for right now, we just want to output white. Okay, so we have our vertex shader source and our fragment shader source. And the next thing that we want to do is we want to go ahead and create the shader. So we want to say this.shader equals new shader, and we want to call, let's just call this one basic. And we want to pass our vertex shader source and our fragment shader source. Okay? And there's one more thing that I need to add to the shader for right now that I forgot to add before. And it's a method of telling WebGL that we actually want to use the shader. So all we've done up to this point is tell WebGL, hey, we've got a shader, here's some source, compile it. But what we actually need to do at this point is we need to tell WebGL, all right, I actually want to use this shader now to actually render something to the screen. So in order to do that, what we need to do is we need a public method called use, and it's going to return a void type. And all this is going to call is gl.useProgram, and it's going to take this.program. That's it. That's all we have to do to use it. But it's important to have that call because we need to tell GL that we actually need to use this shader to draw our stuff. So I'm just going to add a quick comment here, use this shader. Okay. So the next thing that we need to do is, before we actually do our loop, we need to say this dot load shaders, and then this dot shader dot use, and that will let WebGL know, hey, load up the shaders and then mark our shader to actually get used. And so let's go ahead and run this and see what we get. Oh dear. Okay, so why has it done that? What did it return as error? I'm going to set a breakpoint here and just refresh this real quick. What did... Oh, I forgot. It's a empty string, not undefined, so it threw an error and it shouldn't have. Okay, that's my bad. Sorry about that. So instead of checking for undefined here, we just need to replace that with an empty string. Here and here. I believe they both act the same way if I remember correctly. Let's go ahead and run that. And resize. Okay. And we load up here and we've got no errors. So that means that the shader was compiled, it was linked, and used successfully. And it's not really doing anything because we're not passing it any vertex data yet. But we know that the shader is actively being used right now. So that's actually where I'm actually going to stop this video right now. And I'm actually going to go into passing vertex data to the shader in the next video. So thank you guys so much for watching. If you haven't already, consider subscribing, and I will see you guys next time.